Welcome to The Explainer. Today, we're jumping right in to take a microscopic look at the absolute lifeblood of industrial safety over at the Cozy Shack Hicksville facility. We are talking about their ammonia operating procedures plan. Now, we're dealing with a highly hazardous chemical here, anhydrous ammonia, and safely managing it, well, it's not just about, turning a few valves and reading some dials. It requires a flawless, incredibly structured playbook. Whether you're an operator on the floor, a maintenance tech, or the facility manager, understanding the exact parameters of these massive refrigeration systems is absolutely, quite literally, a matter of life and death. So let's break down exactly how this facility maintains total control.
Okay, here's our quick roadmap for today. We'll start with the threat itself, ammonia hazards. Then we'll look at the human element and the roles involved. Third, system boundaries and technical operating specifications. Fourth, daily execution. And we'll wrap up with the ultimate safety net, emergencies.
Starting with Section 1, the threat, ammonia hazards. Let's understand what we're actually up against here. So anhydrous ammonia, or NH3, is definitely not your everyday run-of-the-mill refrigerant. It's a toxic, highly corrosive, and intensely water-reactive gas. It's lighter than air, which is a key detail, because it tells us exactly how it's going to behave in a leak. It'll go up. But what you really need to grasp here is its extreme affinity for water. Think about it. The human body is mostly water. Because of that, exposure to liquid ammonia or concentrated vapor causes instant, incredibly painful, and potentially irreversible damage to your eyes, your skin, and your respiratory tract. It literally burns you by dehydrating and freezing the tissue at the exact same time. We have to treat this substance with the utmost respect. Because those hazards are so severe, the Hicksville playbook uses a highly structured, strict response matrix based on parts per million, or ppm, of ammonia in the air. Just look at how rapidly the stakes escalate. If you're in that 0 to 25 ppm range, a qualified tech with the proper PPE can perform routine repairs for up to 8 hours. But cross that tiny threshold into the 25 to 35 ppm range, your safe window shrinks dramatically down to just 15 minutes. And once you hit 35 ppm, the game completely changes. You have to isolate the equipment and immediately notify the process safety management and EHS managers. You are officially out of routine repair territory. But the absolute crucial point is this specific number right here, 300 ppm. At 300 parts per million, the atmosphere is officially classified as IDLH. That stands for immediately dangerous to life or health. If your handheld meter or the room detectors ever hit this number, the focus shifts entirely away from saving the equipment. It is an immediate evacuation. You notify management, you trigger the emergency action plan, and you get out. No exceptions. Which brings us to Section 2, the human element, roles. Who exactly keeps the facility safe? Because let's be real, a written procedure is just a piece of paper unless specific people actually take ownership of it. Operators are your front line. They execute the procedures and maintain the limits. And the golden rule for operators is this: you are strictly forbidden from bypassing any steps or limits without an approved management of change, or MOC. Then you have the PSM and utility manager. They're the accountable owners of the facility's safety. Maintenance technicians handle mechanical integrity and, critically, those complex lockout-tagout energy isolations. The control room gives you that continuous monitoring and alarm response. And contractors, they don't get a free pass. They are bound to the exact same strict site-safe work practices as the internal team. Moving on to Section 3, System Boundaries, TOS, or Technical Operating Specifications. It's really fascinating to see how these TOS map exact, uncompromising limits to specific pieces of equipment. Let's take the Vilter reciprocating compressor, Unit 2 RCMP-1. Its normal discharge pressure is 175 psig. But if that pressure starts climbing and hits 225 psig, the system logic completely takes over. A high-pressure cutout activates to shut it down to prevent a massive catastrophic failure. Over on the Frick screw compressor, Unit 3 SCMP-1, the normal operating baseline is a bit lower at 150 psig, and its high cutout kicks in at 205 psig. The point here is that operators aren't just out there guessing. They operate on a very strict if this, then that construct, based on these engineered numerical boundaries. Actually, I want to pause for a second and highlight this uncompromising warning pulled directly from the Hicksville initial startup procedure. It says, never exceed maximum allowable working pressure or minimum design metal temperature. Verify relief protection and high-pressure cutouts prior to introducing ammonia. You guys, this isn't a friendly suggestion. It's the absolute ultimate authority of the system's design limits. You do not introduce a highly hazardous chemical until you have proven, beyond a shadow of a doubt, that the safeguards meant to contain it are fully functional. Let's move into Section 4, Daily Execution, Navigating Operating Phases and Permits. An operator can't just stroll up to a massive compressor and hit the on button. They have to methodically work through these unskippable pre-checks. Step 1, you confirm all lockout/tagout devices are cleared and any maintenance permits are officially closed. Step 2, verify the room's emergency ventilation is in standby or auto mode. Your safety net has to be active and ready. Step 3, physically, visually check the compressor oil level right there in the sight glass. And Step 4, ensure the coupling guard is securely in place to prevent any mechanical injury. Only after you've nailed these and several other checks can the actual startup sequence begin. And this perfectly illustrates how the playbook mitigates all these inherent dangers through heavily structured safe work practices, or SWPs. If you're doing maintenance, you don't just, turn off a valve and hope it holds. You execute a complete LOTO procedure and physically try and verify that there is zero energy left. If you are breaking into a pipe, what we call line opening, you absolutely must pump it out and depressurize it first. Confined space entry, that requires rigorous atmospheric testing. And hot work, like welding, that mandates continuous gas monitoring and a dedicated fire watch. You literally cannot perform invasive work without a signed permit verifying these exact safeguards are in place. Which brings us to our final section, Section 5, the safety net, emergencies, what to do when things go wrong. Because we all know the unexpected happens. What happens when an operator rounds a corner and suddenly smells ammonia, or a discharge pressure alarm starts screaming? It is crucial to understand the stark difference between a normal shutdown and an emergency shutdown, or ESD. A normal shutdown is highly methodical. You place the unit in manual, you do a controlled capacity unload, let the suction draw down nice and safe, and then manually stop the compressor. An emergency shutdown, completely different beast. It's triggered by major releases, fires, or totally failed safeguards. It involves hitting an immediate emergency stop button, forced de-energization of the equipment, triggering massive emergency ventilation, and getting the heck out of there. When an ESD is triggered, the sequence has to be executed flawlessly. First, the operator hits the E-stop, which is located safely outside the engine room. Second, they verify that the emergency ventilation has actually kicked on. Third, and this is a really big one, they isolate the liquid supply to the leaking equipment only if they are highly trained and it is 100% safe to do so. If not, scratch that. You skip right to Step 4. Immediately evacuate the area and notify responders via the emergency action plan. Human life always takes priority over saving the equipment. I want to give you a quick sense of scale for the safety systems we're talking about here. 53,000 cubic feet per minute. That is the massive, overwhelming power of the high-capacity emergency ventilation system inside those machinery rooms. And what's truly incredible is that it's programmed to automatically trigger to dilute hazardous vapors if a room detector senses just 5 parts per million of ammonia. Just 5. It's a massive engineering response to the absolute slightest hint of a threat. Now, before we wrap this up, it's really important to acknowledge that sometimes facilities face totally unique situations. Maybe you're running during a massive heat wave with elevated condensing pressures. But you don't just freestyle it. Temporary operations outside normal limits require an approved management of change, period. This means a formal risk review, compensating safeguards, and explicit agreed-upon start and stop time limits. The playbook always demands extreme oversight for any deviation. So we've covered the extreme hazards of anhydrous ammonia, the rigorous technical limits of these compressors, the non-negotiable permits, and the rapid escalation of emergency protocols. This entire playbook exists for one reason and one reason only: to ensure everyone goes home safe at the end of their shift. So the question I'll leave you with today is this: are you prepared to respect the limits, methodically execute the phases, and act instantly when the alarm sounds? Thanks so much for joining me on this explainer, and hey, stay safe out there.